This problem is in two dimensions, and we have a block of wood, hypothetical block of wood, and someone has mounted a rocket on the side of the wood. You'll see a drawing in just a minute. At time equals 0, the wood, which has a mass of 1.8 kilograms, is at rest. Someone's holding it, and it's exactly 3 meters above the ground. The rocket engine that's on the left side is going to be ignited at the same time that the wood is released. The rocket engine is firing horizontally and giving 6 newtons of thrust for a time of 3 seconds. We're going to ignore air resistance in this problem, and we're going to assume that the block of wood remains horizontal as it both falls down to the ground and it moves off to the right because of the influence of the thrust of the rocket engine. You're to calculate the velocity of the wood when it hits the ground. Well, it's a two-dimensional problem. There is going to be a speed in the vertical direction and a speed in the horizontal direction, and we'll combine those to find the vector velocity when the wood hits the ground. So in a minute you'll see a sketch of this, but we're going to do this problem in two parts, as is required for two-dimensional motion. We have to do the calculation in the vertical direction, where there's an acceleration of minus 9.8 meters per second squared, separately from the horizontal motion that has a different acceleration value. The acceleration in the horizontal direction is provided by the rocket motor. It's going to be different in most cases from 9.8 meters per second squared for almost all projectile motion problems you do, two-dimensional problems. So in the situation here, we want to know the velocity when the wood hits the ground. Well, we have some choices to make here. We have a situation, we know it's 3 meters above the ground, and so forth and so on. Would you recommend using this equation to find the speed when the rocket hits the ground, the vertical speed when the rocket hits the ground? Well, we can do this, and I'm telling you, there's more than one way to do this problem. So I'm going to go ahead and work it on this way, but we have a position that's 3 meters below our starting position. I'm calling where we hold the wood up 3 meters off the ground, our start, and 0 for the y coordinate. We're at rest in the vertical motion, so that's a 0. And then we have the situation of 1/2 at squared. The acceleration is a negative number. And we can calculate here the time to reach the ground, 0.782 seconds. This is not exactly a mistake. There's an easier way to calculate the speed when the wood hits the ground. V equals V naught plus AT, but that might not give you enough information to proceed in the problem. So I chose to work through this equation to calculate the time to reach the ground, 0.782 seconds. Well, I'll use this equation, V equals V naught plus AT, and find the speed when the rocket hits the ground. And there's another equation that could be used here. Final velocity squared is initial velocity squared plus 2 times the acceleration times the distance traveled in that vertical direction. And we know the initial velocity is 0. We know the acceleration. We know the distance is going to drop, both of these being negative numbers. And we could find the final velocity that way as well. But since I have the time, I'm going to make use of it here and find the final velocity. I get minus 7.66 meters per second. Using this equation, you'll come up with a positive number when you take the square root. And just physically, from looking at your drawing, it's if, and I should have labeled this, up being the positive direction, from looking at your sketch, as we drop towards the ground, the final velocity has to be negative. So a little bit going on here. Um, but more interesting is in the horizontal direction. So the horizontal motion. Um, we're told that the engine is going to fire for 3 seconds. Um, so, we might be tempted to do final velocity in the x direction is equal to initial velocity in the x direction, the acceleration in the x direction, and the time. To get the acceleration number, we have to do a side calculation here using net force equals mass times acceleration. The net force in the horizontal direction only involves the rocket engine. We do not use the force of gravity as part of the net force. That's in the vertical motion. This motion is only horizontal. I must only use forces and accelerations and velocities that are in the horizontal direction. I don't use any of the y motion except for the time when I do an x calculation. That's the only connection between the y calculation and the x calculation, the vertical calculation and the horizontal calculation. The time number is common to both calculations. Well, here's our acceleration. 6 newtons of force is net force, 1.8 kilograms, so we get 3.3, and it's repeating 3 meters per second squared. I've rounded off. But I have an acceleration now caused by the rocket engine. Well, what's the value of the time when I want to find the final velocity of the rocket? I know the rocket engine is supposed to fire for 3 seconds. I want the velocity when the wood hits the ground. I have to use the time when the wood hits the ground. I do not use 3 seconds of rocket thrust. The wood has impacted the ground before the rocket engine stops firing. And stand back, this wood is on the ground and the rocket engine is still firing, going to make the wood jump around. But 7.782 seconds is the appropriate time in the x calculation. We get this time from the y calculation. Don't use 3 seconds here. We want the speed in the x direction when the wood first hits the ground. We have the acceleration in the x direction. We have the time appropriate until the wood hits the ground. And we can find 2.6 meters per second. And I call off to the right the positive number typically when I do these calculations. So we'll write that here. Now, how do I find the vector velocity? I have the 2 components. I have a y component that's downward, 7.66 meters per second. I have an x component off to the right, 2.6 meters per second. So I know, and I'm going to and reveal all this. We have a triangle here to create. The x motion horizontally, 2.6 meters per second. The y motion down, minus 7.66 meters per second. And we want to know the vector velocity. We want to know the length of this hypotenuse in terms of meters per second. Well, we use Pythagorean theorem. The hypotenuse squared, v squared, is equal to one of the short side squared, 2.6 squared, and then the other short side relative to the hypotenuse. The other short side is minus 7.66 squared. Because this is squared, it doesn't matter if you use plus or minus inside the parentheses there. It is a negative number for the velocity in the y direction. It's a negative, it's downward. But because we're squaring, we're not going to get into trouble. That takes away the negative sign. These 2 numbers, you ought to do this on your calculator. Square them, add them up. I got 65.436. I take a square root of both sides. I find a speed of 8.09 meters per second. Is that reasonable? 8.09 meters per second. In a triangle, the hypotenuse is always the longest side. So I've got a number here, 8.09. It's longer than both of these components. How do I find the angle of this vector, the theta? Well, tangent of theta is opposite side divided by adjacent side. So opposite side is minus 7.66. The adjacent is 2.6. Again, you should check this on your calculator. I came up with negative 2.946. I took inverse tangent of both sides. Inverse tangent of theta produces just theta. The two inverse functions cancel. I just get the argument of theta. In your calculator, if you feed in minus 2.946 to the inverse tangent function, you'll get minus 71.3 degrees. This is correct. We're down from the horizontal. 0 degrees would be the positive x-axis, and we're down 71.3 degrees below the horizontal, and the vector velocity is 8.09 meters per second at an angle 71.3 degrees below the horizontal. So I hope you pay attention to times, the appropriate time to use in the calculations. The time in the x calculation is going to be the same as the time for the y calculation. We only have one object here. As it moves, the object motion in the y direction, time, is the same as the time for the motion in the x direction. When you're doing these projectile motion problems, two-dimensional, the time number is going to be the same. The accelerations will usually be different. Be careful of that. The acceleration in the y direction is usually different than the acceleration in the x direction. For some more example problems and many lectures on physics, you can find the lists with a little description at physics.gpclements.com, and I've also done this for introductory astronomy. The websites have a brief description of the video, if it's a lecture or if it's a problem, how many minutes the video goes, and you can freely access the site. You can freely view the videos on YouTube, but there are links to the YouTube videos at both of these sites, so you can easily find the video that you're interested in. And don't collect email or names. Everything's free. Hope you work some more physics and astronomy problems, and ask your instructor if you have questions.